Okay, very good. Um, Thank you once again for the introduction. My name is Madhavan Swaminathan, go by Swami for short. Been at Penn State now for just 6 months. I spent almost close to 28 years at Georgia Tech before moving here. So the title of today's presentation is Bayesian Learning for Uncertainty Quantification, Optimization, and Inverse Design. I chose this topic based on some feedback that I got from Darby. So hopefully this topic is of interest to all of you. So what I'm going to do today is to take you through some of the basics associated with Bayesian learning and try to apply it in the context of heterogeneous integration. That's one of the areas that I work in, so that you can, on one side, look at the theoretical aspects of things, and on the other side, maybe see its relationship to actual applications. So let me start by introducing this new center that we have at Penn State. So it's called Center for Heterogeneous Integration of Microelectronic Systems, or CHIMES. It's a JUMP 2.0 center. JUMP here stands for Joint University Microelectronics Program. There are 15 universities that are part of the center, with Penn State taking the lead. And you get an idea as to the companies that are supporting us, as well as DARPA. So this center got started beginning of this year. So we're just 6 months into the center. And some of the work I'm going to share with you, I'm going to put it in the context of the center. And the rest of it is work that we did before the center got launched. So what are we trying to do? I'm sure you must have heard the word heterogeneous integration. So we're trying to create this ultra-dense heterogeneous platform that allows us to miniaturize electronics as much as possible. So this is the grand vision that we have. So you get an idea as to the complexity of the semiconductor systems that we're trying to go after, including trying to develop new technologies to support it. So these numbers that you see represents several areas that we are working on. That includes our ability to stack chips on top of each other. Number two is, how do you get power into a system like this? And how do you remove the heat? How do you integrate the millimeter wave electronics as part of this platform? How do you bring in these AI accelerators that are reconfigurable? How do you bring in photonics that allows you to communicate between chips as well as intra-chip, and trying to bring in both passive and active materials as part of such a platform. The reason I show this is, as you can see, this is a little bit futuristic, 10 years out, but you get an idea as to the complexity of the systems that we're trying to go after. And when you try to design systems like these, you run into all kinds of bottlenecks. So I'm going to use that as the starting point here. So if you look at the design of these future complex semiconductor systems, and if you look at the design flow that we have today, there is a big disconnect in terms of what you're able to achieve by making use of the techniques that we have today. So oftentimes when you're trying to go through a design process, you start with some design objectives and certain performance metrics that you have, and then you begin to explore the design space. And that is what is shown over here. And then you try to come up with an initial design, spend a lot of time doing parameter tuning. And then once you feel that the design is okay, you try to optimize it as much as possible. And that's what you tape out. Now, the problem with this kind of an approach is, as you can see, there are lots of these local loops. And the more loops that you have, as you know, things can get very, very frustrating. And oftentimes you end up taping out these very complex designs with errors in them that leads to design respins. And as a result of that, the cost tends to increase quite a bit. So the key takeaways here are that the design space can be large, and exploring trade-offs can be very painful. Now, when you're trying to do design, you're relying on simulators. And these simulators, depending on the type of simulator you're making use of, can be very, very slow. And that can become a major gating factor as you go through the design optimization process, because oftentimes you can get very frustrated, and as a result of that, you begin to take shortcuts. So the question is, how do we address such a complexity moving forward, where things are going to become even more complex while minimizing these design respins? Can machines help ease the process by removing the human from the loop? And that's where we believe machine learning comes in. So I'm going to start with some fundamentals. My apologies if this is something that you already know, but I thought I would put things in context and sort of take you through the fundamentals and sort of build it up so that you can see the value of making use of some of these techniques for very complex applications. I'm sure all of us are familiar with the Bayes theorem, and its representation is shown over here. The fundamental idea over here behind Bayes' theorem is that you have a prior that is shown over here, and then you have a likelihood, and you're trying to combine the two to figure out what the posterior is. So E here represents the evidence, H is the hypothesis. So you're trying to make use of what you know to be able to make predictions. So that is the basic idea behind this. And when you're trying to make use of the Bayes theorem, you're relying on subjective as opposed to objective probabilities. So the more you learn about, let's say, a system, you begin to make different types of decisions. So there's a lot of history behind it. The Bayes rule was proposed way back in 1740 by this Reverend Thomas Bayes, and then it was used later, discovered later by Pierre Simon Laplace in 1774, made use of Alan Turing to break the Enigma code during Second World War. Now, what is different today is that a lot of the bottlenecks associated with the computational side of the Bayes theorem has gone away thanks to these very powerful machines. And when you now combine it with, let's say, machine learning, you can do some very, very interesting things by making use of this Bayes theorem. So I'm going to put this in the context of design and optimization. I call it rethinking design and optimization. So let us say that you're trying to do a design and you are working with a very large design space, and a lot of the problems we tend to work with are very high dimensional problems. And therefore, when you're trying to compute probabilities, looking at it more from a statistical standpoint, these can become very intractable. And this is where we believe if you combine Bayes' theorem with machine learning, it can simplify a lot of the decision-making process. And this is what we call as Bayesian learning here. Now, the second is in the area of optimization, because when you're trying to make use of the Bayes' theorem, you can repose this problem where you're trying to compute probabilities such that it provides you with a direction for the optima, as opposed to the exact solution itself. And what that allows you to do is to very rapidly converge towards the global optimum. I'll show you some examples of that. And in addition to that, you get another very major advantage using the Bayes theorem, and that is to establish these confidence bounds around the predictions, what we call as uncertainty quantification. And I'll try to give you more details on that as well shortly. So let me start with a very simple kind of an example in the context of optimization. So let us say that you have an input and you have an output, and you have 6 data points that maps the input to the output that are given to you. And the question that is posed is, where is the minimum here? Obviously, there is no minimum unless you can find a way to connect these dots to each other. So let us say that you make use of a curve to be able to connect the dots to each other. And based on the nature of this function that you're trying to make use of, or this curve you make use of, you try to determine where the minimum is. In this particular case, the minimum lies right over there, and there is a single occurrence of the minimum. Now, the question is, how do you know that this curve is the right curve that connects the dots to each other? We just don't know. So let's say that you increase the number of those curves. Let's say instead of a single curve, you make use of 5 curves. And for each one of these curves, you figure out where the minima is and figure out also the number of occurrences of that minima as shown over here in the histogram. So once again, 5 curves may not be enough. So let's say you add many curves to it. Now, as you begin to add more and more curves to it, you begin to see that this histogram starts behaving like a function. So you have many instances of the minima, many occurrences of the minima as well. And that sort of gives you an idea as to probably where that minimum is. So what we try to do over here is, instead of trying to make use of many curves, we extend this to infinite curves. And once you extend it to infinite curves, this is what the actual function is going to look like. So you see these dots over here, those represent the 6 data points that you have. And then since you're making use of these infinite curves, you have a certain mean of that function as shown here through this blue curve here. And you also have a certain variance around these, this curve shown here as the confidence bound. Now, this mean of the function shown here is what we call as a surrogate model. And let's assume that these data samples come from a very expensive simulator shown here as a 3D simulator. So they tend to be very few and very expensive to compute. Now, this confidence bound that you have is what we call as the uncertainty of the surrogate. Now, if you look at the histogram, since you're making use of infinite curves, you probably have infinite sets of minima associated with it, and you connect them all together, you end up with a continuous curve or a function, and we call this as an acquisition function. So the goal over here is to figure out where to sample this acquisition function such that you can figure out where you can add extra dots over here to be able to learn more about the system. So this is where the concept of a posterior and a prior comes in, where the concept of subjective versus objective probabilities come in. So the idea here is to be able to minimize the number of black dots over here, which are very expensive to compute, for you to be able to, let's say, come up with the optimum point in your design space. So that brings us to the Gaussian process, which represents the surrogate model. And there is an example acquisition function shown over here. So if you look at the surrogate model, is a Gaussian process. So it has a mean and a covariance associated with it. And the manner in which we compute the covariance is by making use of a kernel. An example of a kernel is a Matern function. There's an entire library of these kernels available as part of the machine learning, in the machine learning community. Now, if you look at this kernel, they tend to have these parameters that we call as hyperparameters. Sometimes it can be a nuisance to work with. Sometimes it can work to your advantage, and I'll show you some examples of that. So these hyperparameters represent adjustable parameters that must be tuned to obtain a model with optimum performance. So if you look at this figure here, you see that right where the dots are, you basically know everything about the system. So there is no variance associated with it. But in between the dots, there is a certain variance associated with it. So at any point along this curve, you can have a Gaussian representation of how that behavior actually looks like. So there is a mean and there is a variance associated with it. Now, if you go to the acquisition function, once again, this acquisition function can be represented in different ways. One example is this upper confidence bound shown here as UCB. And the goal here is to figure out where to sort of sample this acquisition function. So you want to go through an optimization process of the acquisition function itself to figure out where the minima lies so that you can use that as a way to add an extra sample into your surrogate model to be able to learn more about that system. And you go through this process many, many times to be able to converge to the optimum. Now, so if you look at the way we are approaching the optimization problem here, we are trying to move the optimization problem from the original space into a different space, making use of this acquisition function to be able to do all of our optimization. And the assumption here is that this acquisition function, since it represents an analytical function, is fairly easy to compute. That might be true if you're trying to work with low dimensional problems. The minute you get into higher dimensional problems, that can become challenging as well. And I'll try to address some of these issues as I go through the presentation. So how does this Bayesian active learning and optimization actually work? So what we do here is we take the original hard problem. So let us say that you have some input parameter X, and you're taking the function of that. So that becomes the output. And for you to be able to compute these samples tends to be very, very expensive because you're making use of, let's say, a 3D simulator. So this is what we categorize as a hard problem. We just transform this into a series of easier problems that we can make use of, where this U of X that we're trying to optimize is done using the acquisition function. So the flow chart is shown over here. So we start with an initial sample. So let us say that you have one input and one output. Start with a single sample consisting of one single sampled input and the corresponding output. And then we go through this loop over here by creating this Bayesian model. And we continuously keep refining this Bayesian model until we reach the optimal set of parameters. So you can pose this in different ways. In this particular example that we show here as active learning, we continuously sample the most probable promising point to converge to the global optimum. So the goal is not to build this model, but rather to be able to converge to the optimal set of parameters. So when you look at Bayesian learning, you can sort of pose it in different scenarios. I've shown 3 of them here that I'm going to take you through as part of today's presentation. The first is this whole concept of uncertainty quantification. So typically when you try to build a discrete neural network, you assume that any predictions that it makes is always correct, right? And you just don't know if that is accurate or not. So the goal over here is to be able to quantify the uncertainties around the predictions as shown over here through the spread, right, in these curves. The second is the optimization itself. So if you're working with convex types of problems, you can make use of gradient descent. The goal here is to work with non-convex problems where we believe this Bayesian optimization approach can work extremely well. And the third is inverse design. So if you look at the way you can do mapping, you can map the output to the input, but you can also do the reverse. So let us say that you want to be able to map from the output to the input, shown here as inverse design. This becomes extremely useful when you're trying to do a lot of design space exploration, where given a set of objectives at the output, you want to figure out what the input parameters actually are. So let me take you through some of the work that we have done in this area, but let me pause maybe for a minute. If there are any questions, I'll be very happy to answer up to this point.
Doesn't look like there are any in the chat.
Sorry,
Okay.
Can I ask a question?
Yeah, please go ahead.
If you go back one page.
This one here?
No, that the one you skipped over.
Okay.
That one.
Sure.
So data to me is that the output has an uncertainty for a given input, whereas your surrogate model forces every single curve to go through the data points. What happens if you have uncertainty on the data points?
Yes. So the uncertainty I'm referring to is the uncertainty related to the lack of data, right? And the uncertainty related to the neural network model itself, right? And I'll get into the details of that. The assumption here is that the data samples that are available to us okay, is the accurate sample, right? Or in other words, every dot that you see over here represents the truth, right? So we are not questioning that at all. The issue is what happens between those data points and how do we learn more about that system while at the same time trying to quantify uncertainties associated with the availability of data, as well as the model we are making use of, for example, the kernel we are making use of, or the neural network model itself to be able to make those predictions.
Thank you.
Okay, so any other questions?
We have one from the chat.
Sure.
It says, when doing optimization for inverse design, do you have to perform the optimization every time you have a new design target, or does one optimization procedure work for across all design targets?
It depends. So typically when we do optimization, we just start with a sample, and this can be a random sample, and we go through the optimization process. Now, assuming you've gone through it once, you probably have enough information about the system itself. So the next time you do the optimization, it turns out to be a whole lot easier. Okay, so the convergence is a whole lot faster. There are also ways by which you can make use of a transfer learning process to be able to make use of what you have learned to be able to do your optimization. You can pose it in different ways.
And we have one final one in the chat.
Sure.
I'm also curious about this. What are your thoughts on other types of surrogate models, like a random forest instead of just a Gaussian mixture?
Yes. So it depends on what you're trying to make use of these surrogate models for, right? So one of the areas we've been looking at is, let us say that you're trying to work with a very large space where you have to, on one side, do optimization. On the other side, you want to build a model. And you also want to bring in all of the uncertainties associated with your predictions, right? So that's where we're coming from when we talk about this Bayesian learning, right? There are other ways by which you can do that. For example, as I'm sure all know, when it comes to optimization, you can make use of reinforcement learning as well, right? So that's another way by which one can do optimization. So to me, when I look at optimization and look at the other kinds of information that we need to bring in, like uncertainty quantification and things like that, I find this Bayesian learning scheme to be very, very useful. Okay. Should I move on?
I think we have one more, and then I think we
Okay.
can move on.
Sure.
What is your input and output dimension, and do you use surrogate for very high dimensional spaces?
Yes, the goal is to be able to go to very, very high dimensions. And depending on the surrogate model that you make use of, you will run out of steam. And I'll try to address some of these over here, because it's very important to determine the right kernel to make use of. And ultimately that determines the dimensionality of the problem that you can actually address. Hey, let me move on. So I'm going to take you through a series of work that we have done in this area, but also put it in the context of the various examples that we have worked on. These are all related to actual applications. So the first is building a neural network itself, and then trying to combine it with this Bayesian approach. So let me sort of take you through this over here. So what we are trying to do is to be able to learn the frequency response of a structure. And as you know, when you're trying to look at frequency responses, the geometrical parameters of that structure will affect that frequency response. So when you build a neural network to learn what those frequency responses are, there are two ways to do it. One is you include all of your geometrical parameters as well as the frequency as input to a neural network and then make your prediction. Now, when you try to do that, you very quickly will run out of memory, because the number of samples you typically need to be able to look at frequency responses is of the order of thousands or even more. Another opportunity is to be able to move the frequency as an output parameter as opposed to an input parameter. And that is what is shown over here. So we call this technique as the spectral transposed convolutional neural network, spectral for frequency, transposed because we take a typical CNN and just transpose it. And so this STCNN is what is shown over here. So we start with a neural network. It's a fully connected neural network with a bunch of input parameters that we try to learn, and then we flatten it. And then we can go through either 1D convolution or 2D convolution to be able to learn the features associated with the responses. And using those features that are shown here as the latent space, we then try to predict what the actual frequency response is. Now, to be able to bring in or quantify uncertainties, we try to go through this Bayesian dropout scheme. And the idea here is to be able to randomly start dropping some of these neurons to try and capture the uncertainty associated with the model that we are actually making use of. So once again, the uncertainty quantification here represents the model that we are trying to make use of. And so if you look at this approach, it supports parameterization. That is what is indicated here as the various input parameters. The output dimensionality can be extremely high. You're talking about a few million because you're looking at multiple frequency responses. So let me put this in the context of an example. This is a plated through hole and package. So all this is a printed circuit board with different structures like vias associated with it. And there are various parameters that are defined here. And that is what is shown here in the table, right? And each one of these parameters has a minimum and a maximum value associated with it. So that represents the range over which we are trying to train the model. And the output dimensionality is of the order of around 12,000 here. So we are making use of the scattering parameters. So let's look at the response itself. So the first is the prediction. So those of you who are familiar with scattering parameters, this represents the insertion loss. Otherwise, all it is a curve where we are trying to predict what the response actually is. Now, if you look at the black curve, so the black curve represents what comes out of the 3D simulator. So it takes a long time to run and things of that nature. So we're going to assume that that is the truth. And this STCNN predicted represents this dashed line over here. The first thing that you probably say by looking at this is the black line doesn't sit on top of the red curve, which is expected. Now, having said that, if you look at the spread represents the confidence bounds over here, right? And that's a 95% confidence bound. So what we are trying to do here is to be able to predict the mean, but also providing a certain confidence bound associated with it so that the black curve will always sit inside of the spread that is shown over here, right? So that is the key because that allows us to control the amount of data that we are trying to make use of. And assuming you want to be able to reduce the confidence interval itself, you have two ways of doing it. One is you add more data to the code itself, or you change the model. Now, there is another way by which we can quantify this uncertainty, and that is making use of the Gaussian process. And I'll explain that to you shortly. And you get an idea as to the amount of time it takes to be able to include this uncertainty as part of your computations. The extra overhead tends to be quite small. That's what is being compared over here between the base STCNN and the Bayesian STCNN. Now, you can go one step further, and this is where you can make use of the Gaussian process directly to be able to quantify those uncertainties. So if you look at this figure here, what we try to do is to be able to spread the samples around this design space, especially where the variances are high, to be able to improve the confidence bound. And making use of that, we build this model. At the same time, you can also do optimization that is shown on this part of the figure here, where not only are you looking at the variance, you're looking at the mean as well to be able to converge to that optimum. So the key takeaway here is that, using a single sort of a technique, we are trying to approach the global optimum while at the same time building an accurate predictive model. And this code is available through GitHub. If any of you are interested in sort of downloading it and playing with it, please feel free to do so. And if you have any questions, I'll be very happy to sort of help you with it. But one of the key takeaways here is, how do you build this uncertainty around it? And this is what I was alluding to. There are two types of uncertainties. First part of the uncertainty just comes from the data. And the data-related uncertainty is directly captured through the Gaussian process, through the mean and the variances. The second part of the uncertainty comes from the kind of model you're making use of, right? The kernel and things like that. And this is where you're relying on these hyperparameters shown here as theta as a way to be able to tune that model. Every time the design changes or some of those parameters change, that hyperparameter theta has to be retuned. So what we try and do is to try and integrate out this hyperparameters such that we are able to capture the hyperparameter, the change in the hyperparameters as part of our uncertainty quantification process. So this will show up in the confidence bound as well. So it gives you an idea as to what that confidence bound is or what that uncertainty bound is, even when you make changes to the parameters that you're making use of. So this is what I was showing earlier on. So this spread that you see comes from that Gaussian process. But let me also put this in the context of another example. This is in high-speed channel signaling. So here you're communicating between two chips and through the printed circuit board and the package. And there are a few parameters that you've specified with some ranges associated with it. So you're trying to make a prediction. Now, if you look at this graph here, the vertical axis represents the horizontal eye opening. It's one of the performance metrics. And x-axis represents the validation cases or the test cases where you're trying to make the prediction. The actual is shown through the blue line. The predicted is shown through the red line. And as you can see, they don't sit on top of each other. But around this red line, you see the spread. That represents your uncertainty quantification, which gives you that 95% confidence bound. And you'll find that that blue line will always sit inside of the red line along with that spread associated with it. And if you want to improve that confidence bound, as I mentioned earlier, you either change the kernel or fine-tune your kernel or add more data to data samples to your problem. Now, let me pose this from an optimization standpoint. Now, when you look at optimization and you're looking at a large design space, there are a couple of things you want to do. The first is you want to be able to very quickly converge to the region that contains your optimum. That is what we show here as fast exploration and pure exploitation. Fast exploration means that you're focusing more on regions that have a large variance where you can learn more about that system. And pure exploitation is where you're trying to converge to that mean value where the optimum actually lies. Now, as I mentioned earlier, all of the optimization is being done in the acquisition function space. But as the dimensionality of the problem increases there, that itself can become a big showstopper. So what we try to do is to replace this optimization of the acquisition function using a hierarchical partitioning scheme. I'll show you how that works. So this completely eliminates the auxiliary optimization. And the other issue is, how do you know which acquisition function to make use of? Because depending on the kind of design you're making use of, that acquisition function could actually change. So we make use of a library of acquisition functions and we allow the machine to decide which is the best acquisition function to make use of at a specific iteration. So let me put this in the context of clock skew minimization. So let me explain the problem here. We have three chips that are stacked on top of each other. The center chip has a clock distribution network, and the chip on the top of it and below it are logic chips that generate a large amount of heat that creates a temperature gradient across that center chip. And because of that, some of these buffers become super fast, some become super slow. So you create a clock skew. So the goal here is to be able to minimize the clock skew by minimizing the temperature gradient. And these are the input parameters available to you for you to be able to do optimization. So we put this in the context of a black box optimization technique where it doesn't really matter what the input parameters are and what the output parameters are. The goal is to be able to reach that optimum here. And here are the results. So if you look at this figure here, the y-axis represents the clock skew. The x-axis represents the number of multi-physics simulations. Remember, there is a clock skew aspect to it, which comes from a SPICE simulation. And then there is a thermal gradient that we need to compute that comes more from a thermal simulator. So this therefore becomes a multi-physics simulator, and each one of these simulations take a long time. So the goal here is to be able to minimize the number of these multi-physics simulations you want to make use of. And if you look at this convergence curve, especially the blue curve over here, this is typical of these Bayesian optimization techniques. You know, you can get this very, very sharp convergence, which means that very quickly you know where exactly the optimum lies, and then you converge to the actual optimum value. And this kind of a method tends to sort of be much better than other techniques that are non-ML based. That's the green curve shown over here. And it turns out to be much better than some of the Bayesian optimization techniques that have been published in the community. And this is a very key takeaway because oftentimes, depending on the data and the data pattern that you're making use of, and the kinds of problems that you need to solve, you need to make changes to the algorithm itself. And that's exactly what we have done. And you begin to see some of the advantages of this. You get a 4x speed up in terms of the simulation time, and you get a much lower clock skew compared to other machine learning methods that are available in the community. So one of the questions that was asked is, how do you address dimensionality, and especially higher dimensionality? And this is a very, very important question to address, because when you build these surrogate models, as I was mentioning earlier, based on the kinds of kernels you're making use of, you will reach an upper limit. And this is one of those examples where we had to make changes to the kernel itself, shown here as the additive Gaussian process, to be able to go to higher dimensionality compared to the previous technique that I showed you. So here, as you can see, we make use of this additive Gaussian process to be able to capture the first order, the second order, the dth order interactions. Now, I was mentioning earlier about optimization or removing the optimization of the acquisition function. So the way we do that is by making use of a tree-based technique. So these are the various samples that we quickly evaluate and determine exactly where the next sampling point needs to be. So this is part of the sampling strategy that once again completely eliminates the optimization of the acquisition function itself. And this is very important when you're trying to go after higher dimensionality problems. And this code is also available through GitHub if any of you are interested in using it. So let me now scale the dimensionality. Remember, the previous example had a dimensionality of 5. So let's say we want to increase it to 32. And this is an example of an RF wireless power transfer system. So you have an RF input and a DC output, and in between you have some layouts, you have some circuit components that you're trying to optimize, and the number of parameters is 32. And if you look at this example, there are two parameters at the output that we were interested in. One is the coil area of the receiver, that is this coil that is shown here. And the second is the system efficiency. You want that to be as high as possible. So when you do this multi-objective optimization, you can determine which one of these parameters is more important for you, right? So you can basically weight it. And that's exactly what we did over here. And once again, you see this convergence very quickly. You can figure out where exactly the optimum lies and try to converge to that optimum value. And then you get some very nice system efficiencies along with a reasonable RX coil area. Now here is some work in progress. This is work that we're doing with DARPA. And the problem here is that you have a computer rack, okay? And DARPA is very interested in figuring out exactly where, let's say, the maximum electric field lies when you have an impinging plane wave, let's say that is coming from the bottom, that is impinging on this computer rack, so that it gives them an idea as to where exactly to place their computer system, right? So this stuff that you see bouncing around represents, let's say, a computer, right? And what this basically shows is that how this, this object moves inside of that rack until it reaches a position where the electric field is a maximum, right? And clearly, as it moves, there's a lot of interaction going on between the scattered field inside of the rack and this object as well. And once again, you see this convergence plot, which is very typical of Bayesian learning. So it turns out that the maximum electric field is at the top left corner of this rack, and that represents the final solution here. You can also apply this to floor plan and placement, right? So this is what you would typically do when you're trying to do very early design, where let's say you have a bunch of chips that you want to place such that you reduce the overall area, while at the same time you want to make sure that your temperature gradient is as small as possible, so, and as well as the temperature, the hotspots are as low as possible. So you can make use of Bayesian optimization here as well. And let me just sort of explain the problem to you over here. So you have a bunch of chips that you're trying to connect together. You're placing them on a printed circuit board, and then you have some material, let's say, that you're adding on top of it. So there are two kinds of parameters that, or three kinds of parameters that you're trying to work with, or four types that are shown here. One is the die thickness, and the second is the thermal conductivity of the materials you're making use of. These are the continuous parameters. You also have the categorical parameters, where you're trying to figure out the number of layers you need to have to be able to connect the chips to each other, as well as whether you need to keep these dies exposed or cover it using this mold material, right? So this is once again an interesting problem, because when you're trying to look at placement of these chips in the past, people have made use of simulated annealing. You can now make use of Bayesian learning as well, and that is the concept that is shown over here by relying on the mean and the variances of the Gaussian process. And here are the results. So, the kinds of convergence plots, once again, are very typical of what you would see for Bayesian optimization. And the key here is that we are able to look at the effect of both the chip as well as the package in terms of determining what that optimum value is, in terms of coming up with an optimized floor plan that also has the minimum temperature associated with it, right? So once again, it's a multi-objective kind of an optimization problem. So let me just cover a couple of more slides, and then I'll pause. If there are any questions, I'll be very happy to answer. So let's look at, once again, another type of a problem that arises in microwave design, and this is a high-dimensional problem, right? Now, when you're trying to make use of acquisition functions that are hard to optimize, and let's say for whatever reason you're not able to make use of this tree-based approach, the question is, what do you do? Now, there are various ways by which you can address this problem, and one of it is to make use of these hyperparameters that are part of your kernel to be able to do a sensitivity analysis, right? So if you look at this kernel, this is the Mattern 5.2 kernel, and if you look at this hyperparameter, that's a length scale parameter, and depending on the dimensionality of the problem, let's say it has dimension D associated with it. Now, as you do the optimization, you can make use of this parameter to be able to rank the parameters based on their sensitivities. And that is the concept that is shown over here. So if you look at this very simple function, this has a dimensionality of 2. You see sigma 1 has a value and sigma 2 has a different value. The smaller valued sigma corresponds to the parameter that has higher sensitivity as opposed to the output response. Now, this becomes very useful when you're trying to go after higher dimensional problems, because now, based on the sensitivities of these parameters, you can build a lower dimensional Gaussian process model, right? Where the rest of the parameters are included as noise, and then you make use of a lower dimensional acquisition function to be able to do all your optimization, and then bring in the rest of the parameters later on in your optimization process. So we have applied it to an antenna design. This is a millimeter wave antenna design. And if you look at this figure over here, so what you have is a Butler matrix that changes the phase shift to these antenna elements. And there are various parameters associated with it in this design that we are trying to tune. So you can now specify an objective function. So all these equations represent the direction in which you're trying to point your beam. And your goal is to be able to minimize the amount of power that gets into the side lobes, right? When you're trying to radiate out this energy from this antenna array. So here are the results. So if you look at the parameters, there's a long list of parameters that we're trying to tune, right? Now, if you look at this histogram over here, the vertical, the height of this histogram gives you an idea as to how sensitive that parameter is. So if you rank all of these parameters from a sensitivity standpoint, you can figure out which are the most sensitive parameters. So you focus on these parameters to be able to do your initial optimization and then bring in the rest of the parameters to be able to complete your optimization as well. And that is the curve that is shown over here in terms of the convergence plot. So if you look at the modified BO, right, and compare it with the green line, which is the typical Bayesian optimization, you see that a big advantage in terms of efficiencies, simply because we go through a two-step process to be able to address these problems that have high dimensionality associated with it. And here are the results. So the key takeaway from this is this represents your main lobe. You want to make sure that the power that is coming out of your side lobes are as small as possible. And you also see a comparison between this modified BO, which is this red curve over here, and its comparison to this green line, which represents the typical Bayesian optimization. So let me pause here. I think I'm running out of time, but if there are any questions, I'll be very, very happy to answer.
In the chat, we have a question. What are your thoughts on approaches such as Bayes flow?
Can you repeat that one more time? Yeah.
What are your thoughts on approaches such as Bayes flow?
Bayes flow in what context? Can you elaborate on that if you don't mind?
Michael, I'll ask you to unmute if you want to elaborate.
Mm-hmm.
Michael cannot unmute, but they are a new class of likelihood-free models for inverse problems.
Oh, for inverse problems. I'm going to get to inverse problems shortly. Maybe I can address some of that. Yeah.
Okay.
Should I move on now, Darby? I have 8 minutes left, so maybe I'll spend 3 minutes just to define the problem and the solution, and then maybe I can take some questions, okay?
That sounds good.
And that is in the area of inverse design. So far, everything I've sort of covered is the forward process where you have some input parameters and you have some output parameters and the two are mapped to each other through a function or a function of functions and things like that. The inverse problem is where, given the output, you're trying to figure out what the input is, right? And this poses all kinds of challenges. One is the existence itself. Does the inverse even exist? And the uniqueness of the solution, as we all know, there could be cases where multiple sets of input parameters can give you the same output. So how do you determine what is the uniqueness of the solution? And that's the concept shown over here, the inverse process, where you can have this very ambiguous mapping. So how do you address something like this? So first of all, if you try to build a typical neural network, invariably it will not be invertible. So you have to focus on neural networks that can be invertible, which means that these are neural networks that you can make use of to go both in the forward direction as well as the reverse direction, right? So there are some issues associated with it. One is what we call a stochasticity. The second is the construction. So if you look at the way we create this neural network, you'll find that, this kind of an architecture allows you to propagate the data both in the forward as well as the inverse direction because of the nature of this connectivity that is shown over here. So if you look at these S&T functions, these represent feed-forward neural networks. So there is no requirement to compute their inverse at all based on the architecture that is shown over here. So what that allows us to do is to train this neural network in the forward direction and use the same neural network in the reverse direction as well to be able to do the inverse design. So the way you put this together is in the following way. So let's say that you've created this neural network here, right, consisting of these coupling blocks. You have a set of inputs. You go through the forward process and you create the output, right? So this gives you a mapping between the input and the output. But then as you go through this mapping process, there is probably some lost information. We capture that lost information through this latent space shown here as Z, right? And then when we do the inverse design or the inverse estimation, we make use of the output along with this latent space to be able to predict what the input is. Okay, so if you look at the structure of the neural network, you have to make sure that the dimensionality at the input and the output are the same. And that is the reason why we pad this with zeros, either on the input side or on the output side, so that we keep the dimensionality the same. Okay. And the manner in which you create these S&T functions, it depends on the kind of neural networks or the kind of data that you're actually making use of. So let me just show one example, and I'm going to stop. So this is an example of the inverse design of an SIW filter in D-band. So you have a structure over here, and let's say that there are two output specifications. One is the passband center frequency, and the second is the roll-off. And you have a set of input parameters, just two here, slot width and slot depth. So your goal here is, given these parameters, you want to be able to estimate what these input parameters are. Now, as you go through this process, as I mentioned, you want to make sure that the dimensionality at the input and at the output are the same. So you have the two input parameters, you have the two output parameters, then you have the two latent parameters corresponding to these two input parameters, right? And now you have to make use of padding to make sure that the dimensionality is the same on both sides. Now, when you do the inverse solutions, everything is in the context of probabilities, right? So if you look at this figure over here, so you have some kind of a distribution, both for the slot width as well as the slot depth that you're trying to compute. And if you look at these two stars over here, those represent two possible candidates that gives you the kind of outputs you're interested in. So these represent the input parameters. Now, what is interesting is that if you take those 2 points, those 2 solutions, and actually do a simulation and plot the response, you'll find that one of these solutions is what a designer would have come up with. The other one, is probably something that is completely out of what a typical designer would think about. And that solution that the machine came up with actually gives you much better performance compared to what a hand-tuned design would have given us. And that is the key here, because through this inverse design process, you can basically come up with multiple instances of the solution and pick the one that you think would actually work for you, right? And this can be done almost on the fly. So let me stop here. I have one more example to show, but I don't think I have the time for it. But if there are any questions, I'll be very, very happy to answer.